Peradaban dunia terus bergerak ke arah yang kian modern. Namun, kemajuan peradaban juga menghadirkan tantangan baru yang perlu dicarikan solusi. Pemenuhan kebutuhan pangan, kualitas kesehatan dan lingkungan hingga kebutuhan optimasi potensi sektor strategis menjadi tantangan utama dalam pembangunan berkelanjutan di era yang modern ini. Ilmu pengetahuan dan teknologi atau iptek hadir sebagai bagian solusi bagi tantangan peradaban modern tersebut. Teknologi nuklir sebagai bagian dari iptek berkontribusi menghadirkan solusi di banyak sektor strategis pembangunan. Melalui Badan Tenaga Nuklir Nasional Batan, berbagai inovasi teknologi nuklir untuk tujuan damai terus-menerus dilakukan, menghadirkan solusi, menjawab tantangan peradaban untuk kemajuan Indonesia. Dibentuk pada tahun 1958, Batan pada awalnya memiliki misi untuk melindungi segenap rakyat Indonesia dari cemaran radioaktif akibat penggunaan senjata nuklir. Selama 6 dekade terus berkembang dengan dinamis dalam hal struktur, fasilitas, program maupun hasil penelitian yang telah dicapai. Batan telah menunjukkan berbagai capaian dan prestasi dalam membuat terobosan dan inovasi di bidang teknologi nuklir. Mendukung peningkatan ketahanan pangan nasional, beragam varietas unggul tanaman pangan telah dihasilkan dan dimanfaatkan oleh masyarakat di sebagian besar wilayah Indonesia, berkontribusi terhadap peningkatan perekonomian pada skala mikro dan makro. Mendukung peningkatan kualitas layanan kesehatan masyarakat. Inovasi teknologi nuklir menghasilkan peralatan dan farmaka untuk deteksi dini penyakit, bahan obat penghilang rasa sakit dan terapi, hingga penyediaan jaringan biologi steril untuk berbagai tujuan, pencegahan infeksi penyakit, penyembuhan luka bakar, dan penyediaan tulang steril untuk operasi ortopedi. Mendukung kemandirian energi nasional, Batan melakukan kajian kelayakan nuklir sebagai salah satu sumber energi pembangkitan listrik, studi calon tapak potensial, aspek keekonomian, aspek keselamatan, aspek desain, aspek penerimaan masyarakat. Penguasaan teknologi reaktor juga dilakukan dengan mengembangkan desain reaktor daya maju yang sesuai karakteristik kebutuhan energi nasional. Mendukung sektor industri nasional, Batan mengembangkan teknik iradiasi untuk meningkatkan kualitas komoditas produk domestik seperti bahan pangan, bahan farmasi, bahan kosmetik, bahan herbal, dan alat medis. Inovasi juga dilakukan untuk menyediakan teknologi terkini dan mendukung peningkatan kualitas SDM bagi pelaku industri uji tak rusak. Berkolaborasi dengan institusi lain, Batan juga turut berperan dalam pengembangan industri strategis berbasis logam tanah jarang. Mendukung upaya pelestarian lingkungan, Batan menghadirkan teknik analisis unsur polutan yang berkontribusi dalam kebijakan sektor lingkungan, serta menghadirkan teknologi untuk pemetaan dan optimasi sumber daya strategis seperti air, panas bumi, minyak, dan gas. Kesuksesan Batan dalam menghasilkan beragam inovasi litbang jasa teknologi nuklir telah dibuktikan dengan diterimanya berbagai penghargaan tertinggi oleh Batan, baik dari dalam maupun luar negeri. Tidak hanya menghasilkan produk dan teknologi, Batan memberikan layanan jasa pada masyarakat, di antaranya pendidikan, pelatihan dan sertifikasi person, analisis unsur, kalibrasi alat, serta pengolahan limbah radioaktif.
Ketika Presiden Soekarno mendirikan Badan Tenaga Atom Nasional, tujuan beliau adalah ingin bahwa teknologi nuklir waktu itu masih bernama atom bisa bermanfaat banyak untuk masyarakat. Di samping itu juga ada cita-cita beliau adalah membawa Indonesia ke dalam kancah level tertinggi di bidang sains dan teknologi. Namun lebih dari itu, ketika Bung Karno ingin nuklir diintroduksi di Indonesia adalah bisa menjadi kekuatan bagi bangsa ini untuk lebih maju. Ada unsur untuk mencerdaskan masyarakat, ada unsur kemandirian, dan juga ada unsur kita bisa mampu bekerjasama dengan banyak negara lain berbasis pada teknologi nuklir untuk tujuan damai. Untuk itulah selama 60 tahun Badan Tenaga Nuklir Nasional bergerak terus-menerus bagaimana mengembangkan dan memanfaatkan teknologi ini. Itu diimplementasikan dengan beberapa kegiatan yang kita lakukan di bidang pertanian, pangan, industri, lingkungan, maupun cita-cita kita di bidang energi. Kita bekerja sama dengan 24 daerah, kita juga melakukan suatu diseminasi maupun promosi hasil-hasil teknologi tersebut. Manfaatnya sudah dirasakan oleh sebagian masyarakat. Tapi di sisi lain kita juga ingin unggul di tingkat regional. Kita melakukan kerjasama dengan banyak negara, bahkan melalui kerjasama selatan-selatan, dan kita ditunjuk oleh Badan Tenaga Atom Internasional sebagai Collaborating Center untuk memberikan bimbingan banyak ahli di kawasan Asia maupun bahkan sampai Afrika. Inilah hal yang kita lakukan. Di sisi lain kita juga ingin mencerdaskan masyarakat, ingin mencerdaskan bangsa ini. Maka fasilitas-fasilitas nuklir yang ada di Batan, terutama 3 reaktor nuklirnya, ikut mendidik bangsa ini. Ada banyak ribuan S1, S2, S3 yang telah dihasilkan oleh fasilitas kita. Itulah cita-cita yang sudah diamanatkan oleh pendiri bangsa ini Bung Karno 60 tahun yang lalu.
Tantangan dalam pengembangan teknologi nuklir akan selalu ada. Namun demikian, Batan akan tetap berkomitmen untuk menghasilkan teknologi yang diperlukan oleh masyarakat dalam mendukung pembangunan berkelanjutan.
Selamat malam Bapak Ibu sekalian. Terima kasih sudah hadir dalam webinar. Kita masih punya 20 menit sebelum acara utama.
Saya sedikit ya.
Nuclear energy, nuclear medicine and radioisotope production, mining exploration and exploitation, nuclear application and agricultural activity, cultivation sterilization, nanotechnology, National Atomic Energy Commission of Argentina. The National Atomic Energy Commission of Argentina is developing its first nuclear power plant totally designed in Argentina, the prototype CARM-25. The facility will be located a few kilometers from Lima, province of Buenos Aires, next to Atucha 1 and 2 nuclear power plants, and it will generate in the order of 25 megawatts. The nuclear industry has the highest quality and safety standards worldwide. In accordance with this, the National Atomic Energy Commission of Argentina assumes the construction of CARM, respecting the highest safety requirements such as the anti-seismic structure. The CARM main building will have a surface of 20,000 square meters and will be built with the most modern materials. The control room is one of the most important areas of the plant. It will have cutting-edge technology. All the functions will be monitored, including pressure and temperature inside the reactor, core power, and the state of fuel. CARM plant operators will carry out control functions that double reactor safety measures, since practically all its functions are automatic. The pressure vessel stands at the heart of the building, 11 meters high by 3 meters diameter. It's located inside a wide concrete and steel containment, which guarantees that the entire process will be kept confined to this area, reducing the possibility of leakage to the environment. The primary circuit of a nuclear power plant is the system of water circulation that cools the core. The secondary circuit, another independent water circuit, generates the steam that will move the turbine. CARM integrates the primary and part of the secondary circuits to the pressure vessel, reducing the amount of pipelines and consequently the probability of a loss of coolant accident. LOCA. This integration inside the vessel is one of the distinctive features of CARM, ensuring that the water that acts as a core coolant will never escape from the pressure vessel, increasing the safety level. CARM operation takes into account fuel element replacement every 18 months. The fuels will be withdrawn from the pressure vessel using special tools, and then will be placed into a dedicated pool. Once the fuel is sufficiently cold and stable after several years in this pool, it will then be sent to a safe and final disposal. Nuclear fission is a process by which certain minerals such as uranium are fragmented, releasing a great amount of energy. By being fragmented, each uranium atom emits neutrons that at the same time impact on other atoms. These in turn are split and release more neutrons, continuing in this way into what is known as a chain reaction. The chain reaction is controlled by means of the insertion and withdrawal of the control rods. These are made of a material that absorbs the released neutrons traveling within the vessel. Some of these rods remain suspended above the core, and if necessary, fall by the pull of gravity. The rods are thereby totally inserted into the fuel elements and shut down the reactor within 2 seconds. Due to the heat produced by the nuclear fission process, when the water passes through the core, it is heated and moves upwards into the pressure vessel until it reaches the upper sector. It then flows downwards along the walls, leaving part of that heat in the integrated steam generators. It returns to the bottom, now cooler than before, where it will be warmed once again, and the process is then repeated. This is called natural circulation, and through this process, the water moves due to the changes in temperature. Therefore, the use of pumps or other devices is not required. This fact simplifies the design and makes the system safer. By being warmed through contact with the water of the primary circuit, the water of the secondary circuit turns into steam and generates the necessary strength to move the turbine. Then it is cooled down with a tertiary circuit that is filled with water obtained from a river or lake. The steam is cooled once it has passed through the turbine, turning into water and repeating the process once again. Electrical generation is similar to that which is obtained through conventional plants such as hydraulic or coal. The turbine rotation causes a generator to move. It is this generator that produces the electrical energy that is destined to supply our homes. The main difference with other plants is the way in which the steam is generated. In all nuclear plants, this is achieved by heating water through the controlled fission reaction of the uranium. CARM has passive systems as its main safety features. That is to say, they act with no external power supply, and they have the capability of self-operation without human intervention for more than 36 hours. CARM also has active systems that are redundantly fitted, with defense in depth that prevents the dispersion of radioactive material thanks to 3 barriers: the metallic structure of each fuel element, the pressure vessel walls, and the concrete and steel containment that surrounds it. With more than 60 years of history, thanks to the efforts and dedication of scientists, engineers, technicians, and specialists, combined with the participation of its associated firms, the National Atomic Energy Commission of Argentina has designed, built, and operated more than 10 research reactors. It has also been involved in the construction, operation, and maintenance of Embalse and Atucha 1 and 2 nuclear power plants. This experience enables the National Atomic Energy Commission of Argentina to build the nuclear plant of the future. CARM.
Selamat malam, Bapak, Ibu sekalian. Ini ada Pak Dedi, Pak Alvano, Bu Lili, dan lain-lain. Banyak sekali. Ada, ada Pak Ari Purwanto. Gimana kabar Pak Ari?
Alhamdulillah.
Assalamualaikum Pak Jarod.
Waalaikumsalam.
Tambah muda ya.
Oh iya, aku memang masih muda. Memang ini masih. Etok wae kuwi.
Assalamualaikum Pak Jarod. Selamat
Pak
malam.
Utomo, selamat malam.
Pak.
Gimana kabar?
Sehat Pak ya, sehat ya, segar.
Alhamdulillah, harus segar.
Rambutnya gila.
Oh, iya harus gitu kan.
Rambutnya klimis.
Oh, iya harus klimis toh.
Kelihatan bedanya Pak Jarod.
Itu permintaan istri supaya tetap klimis gitu kan. Kalau WFH di rumah itu letek itu kan jelek banget itu kan. Bikin istri marah terus.
Selamat malam.
Selamat malam Pak. Pak Utama Kajo.
Ya,
Moga-moga tidak terlalu malam ya. Ini biasanya katanya Pak Utama.
Kalau matahari nggak ada terus drop Pak. Rambutnya bagus nih malam.
Saya udah pangkas ini Pak Utama ini.
Biasanya jelek ya.
Kemarin gondrong ini. Hello Dario, are you there?
Yep.
Yeah. You're ready. Okay, thank you. There are many Indonesian participants here, and maybe first I will have 5 minutes or less to speak in Indonesian language. Then after that, we begin the webinar using English. Hopefully, we will start 7:30 p.m. here, but 9:30 a.m. in your country. How is the weather in Argentina right now, in your place?
Rainy.
Oh, rainy. Okay. So the temperature is cold or?
Yeah, we are finishing winter.
Mm-hmm.
And we're expecting to have the weather improving next weeks.
Okay, so because you are in the southern hemisphere, it means different with the Europe or North America.
You have winter where you have summer.
How cold the winter?
Well, here in the south of Argentina is a ski center, and we have snow, but the temperature is about 0 degrees.
0 degrees. Wow. So for Indonesian, it means very cold because here is 25 until 30 degrees Celsius.
Yeah, I understand. But in Buenos Aires, that is about 1,500 kilometers away from Bariloche, and then never snow.
Never snow.
Never, okay. In Buenos Aires, never snow.
Okay. So, although never snow, but still cold, isn't it?
It's much warmer than Bariloche.
Okay. Yeah, okay.
COVID gimana Argentina?
Pak Dario, where is the city of in Argentina? In Buenos Aires or?
No, Bariloche. Bariloche is close to the Andes. The Andes are the highest mountains in South America. In the south, in the northern part of Patagonia, so it's about 1,500 kilometers southwest of Buenos Aires.
Oh, okay. So that's small city or big city?
It's a city of about 150,000 people.
Oh, 800. Okay.
No, 100.
Oh, 100. Oh, it's very small city.
Yeah, it's small, and the closest city that is larger than us is 450 kilometers away from us.
Okay. Oh. Okay.
Free from COVID, yeah.
How about the COVID-19 in your city, in your town? Still high?
What about?
The virus COVID, the Corona-19.
Well, we in Bariloche in Argentina is growing, but in Bariloche it's quite stable but high, still high.
Oh, okay. That's very. So it's mean you mostly work from home, or sometimes you have to go to.
Yeah, at the office, the shops are open, but mostly the people is not allowed to go to the office.
Okay. Oh. So how about you?
I work from home, and sometimes I have a special permit to go to the office.
Oh, okay. I think almost the same with us. Okay, Dario, we will start right away. I will speak first in Indonesian language. Bapak Ibu sekalian, selamat malam. Kita bertemu kembali ke dalam webinar kali ini yang ke-17 terkait dengan prototipe PLTN Argentina. Mungkin banyak yang tidak mengenal, hanya sebagian kecil dari teman-teman di Batan saja mungkin yang mengenal bagaimana Argentina itu mempunyai kekuatan teknologi nuklir. Mereka mengekspor reaktor risetnya ke Australia, ke Mesir, ke Aljazair, ke Belanda, dan banyak negara lain. Jadi punya kemampuan teknologi nuklir yang luar biasa. Meskipun demikian, mereka menggunakan PLTN besar dari Jerman dan Kanada. Nah, dalam hal ini mereka ingin membangun kemampuan PLTN mereka dengan memulai prototipe namanya KARM 25. 25 itu berarti daya netnya 25 MW. Nah, ini prototipe atau purwarupa yang kelak kalau berhasil, dan menurut IAEA atau Badan Tenaga Atom Internasional adalah salah satu dari 3 SMR yang sudah beroperasi maupun dalam waktu dekat beroperasi. Yang sudah beroperasi adalah PLTN terapung Rusia, yang tahun depan beroperasi adalah HTRPM Tiongkok, dan berikutnya adalah KARM 25. Nah, sebagai prototipe nanti kita akan bisa melihat setelah itu ada tindak lanjutnya, yaitu mereka ingin membangun yang lebih besar, 100 lebih, 120, dan itu berskala komersial. Jadi roadmap mereka atau rentang waktu yang mereka lakukan dari mulai bisa membangun reaktor riset sendiri, kemudian membangun prototipe PLTN mini mereka, dan kemudian kelak bisa membangun yang lebih besar, bisa kita tiru. Ini bentuk dari suatu kegiatan kemandirian mereka menuju negara yang mampu berkontribusi di kancah internasional. Mungkin nanti akan ada yang bertanya, berapa biayanya dan sebagainya. Sebagai prototipe atau purwarupa tentu saja tidak bisa dibandingkan dengan PLTN yang besar yang sudah komersial. Tetapi ini menjadi salah satu andalan dari Argentina kelak dalam hal ekspor teknologi nuklir mereka atau PLTN mereka ke dunia internasional. Sebagai langkah awal, saya akan menunjukkan sebagai video pembuka terkait HIMNI. Good evening, ladies and gentlemen, dear colleagues in Indonesia. Good morning for our colleague in Argentina or other country in American continent, and good afternoon for our colleague maybe in Europe and other parts of the world. Today or this evening in Jakarta, we have a special webinars discussing about the Argentines KARM 25. This is a SMR series that we have already held before. At first, we invite the Russian, the floating NPP, around a month ago. Then 3 weeks ago, we invite the Chinese HDRPM. The professor from Tsinghua University already gave us the background and the target and everything about their HDRPM. This time, it is honored for us that we have a speaker, Mr. Dario Demastro from Argentina, to speak about the mini NPP, the prototype of NPP. It is called Kerem 25. But before we start the webinars, I would like to ask Mr. Dr. Ari Rahmadi, the representative of Indonesian Nuclear Society, to give an opening speech. Please, Pak Ari.
Thank you very much, Pak Jarod. My name is Ari Rahmadi from Indonesia. I'm working for BPPT, the Agency for the Assessment and Application of Technology. Tonight, your time will be morning, right? I'm representing the Indonesian Nuclear Society, a society that comprises many members from various backgrounds, including the one from Bataan, academician, and even the non-governmental organizations. Today, I think this is a good time to review the potential of the nuclear power plant for, I think this is for the world as well as for Indonesia. In particular, that Indonesia comprises many islands, and as you see, that many islands tend to have a small scale electricity generation systems. It could be about 25 megawatts, 100 megawatts, and since Indonesia has major islands, only Sumatra and Java, those 1,000 megawatt typical steam power plant only situated in that region. So I believe having an alternative of nuclear power plant for distributed generation in Indonesia comprises many islands would be a good alternative for power generation in Indonesia. So I don't want to talk more about Indonesia, but I'd like to hear more about the Kerem 25 megawatt here. So I guess welcome to this webinar series, and thank you, Pak Jarod, for having me. And I would like also thank you for the Argentine. I forgot his name is, but Mr. Demastro, am I correct? Yeah.
Yeah, Pak Dario. You can call him Dario.
Oh, Dario, Mr. Dario, for attending this webinar series. It is late in our time, but it's morning in your time. Thank you very much, and I appreciate it. Thank you, Pak Jarod.
Thank you, Pak Ari. Before we begin the presentation of Dario, I would like to read his CV. Mr. Dario Del Mastro is the engineering manager of Kerem, so he's in charge of Kerem. He's a member of the technical working group. In the agency, there are two: the advanced technology for light water reactors and the small, medium, or modular reactors. He is also the professor at Instituto Balseiro. He was the head of the thermal hydraulic group at Centro Atomico Bariloche, and he obtained his engineer and doctoral degree in nuclear engineering from Instituto Balseiro. So it's time to invite Mr. Dario Del Mastro. Please, Dario.
Thank you. Thank you for the invitation. I will try to share my screen. Okay, can you see the screen properly?
Not yet. Yes, okay.
Okay, I will speak slowly. Thank you for the invitation. I will tell you a bit about the progress of the current 25 construction, and I will tell you this prototype, what are the main characteristics, and what is the whole plan for the Argentinian development of this SMR. First, I will start telling you a bit about the Argentinian story. Argentina is not a well-known country in nuclear, so I will tell a bit about us. Since 1950s, Argentina has developed and constructed research reactors. This activity was very successful, and research reactors were or are being exported to different countries. We have exported, as they have said, to Australia, Algeria, Egypt, recently to Kingdom of Saudi Arabia, and we have recently sold the detailed engineering of a research reactor to Brazil, and we have sold the basic engineering or conceptual engineering to Netherlands of another research reactor the last year. So we have a broad experience in this, but this is the result of a work during several decades, an accumulative work during several decades to develop and establish this capability. Argentina has also 3 pressurized heavy water reactors, 3 nuclear power plants in operations. The participation of the local industry in the construction was very important. Even in the 1980s, Argentina has designed pressurized heavy water reactors, but they have never been reached the level of current, and they were discontinued. I can tell you that in the 1960s, Argentina decided to build heavy water nuclear reactors to use natural uranium because Argentina didn't have the capability to enrich uranium. So that was the reason why we have 3 operating nuclear power plants using heavy water as modulator. We can see here where the 3 nuclear power plants are. One is a Candu type nuclear power plant, and the other 2 are quite particular nuclear power plants. They are heavy water, but with a pressure vessel. So they are, from outside, they resemble a PWR, but they have heavy water inside, so they are unique kind. They are a German design, and the last one, Atucha 2, was finished less than 10 years ago. And as the designer, Siemens, has quit the nuclear business, the Argentinian companies need to arrange all the things and to take the responsibility, and we're in charge to finish the nuclear power plant that is successfully operating now. At the same site where Atucha 1 and Atucha 2 is operating, we are constructing the prototype of current 25. Argentina produced nuclear fuels for the nuclear power plants in operation and also for the research reactor. Many nuclear fuel cycle plants were built during this decade. In the early 80s, Argentina developed the uranium enrichment capability. That was a key point because having the technology to enrich uranium, we allow to start the development of a reactor based on enriched uranium like a PWR. And current, we will see, basically is an integrated PWR. So this was a very important key issue. During the 90s, the enrichment capability the enrichment activity were stopped, but 10 years ago, 15 years ago, we have resumed enrichment activities at a laboratory scale to keep the technology and the operating teams ready to go. So let's talk now about Karen, and let's talk about the project. Karen project consists of the development, design, and construction of a small nuclear power plants based on integrated pressurized water reactors. We will see later what is an integrated pressurized water reactor. This project allows Argentina to sustain activities in the nuclear power plant design and construction area, assuring the availability and updated technology in the midterm. The design basis is supported by the cumulative experience acquired in the research reactor design, construction, and operation, and pressurized heavy water reactors, nuclear power plant operation, maintenance, and improvement, as well as the finalization of Atucha 2 and the development of advanced design solutions. Aims to export nuclear power plant in a competitive market, like to previous experience in research reactor. So our target is to develop a product like we have done with the research reactor and to be competitive to export it to other countries. It's important that the cost and the money involved in building SMR is quite similar, it's not the same, but quite similar to the money involved in building a large research reactor. Well, let's make a comparison between PWR and Karen. On the left side, we can see classic PWR. We can see the pressure vessel, the steam generators, the pressurizer, the main pumps, the control rod mechanism. In the right hand, we see Karen. We have only one pressure vessel and all these components inside this pressure vessel. The operation of a classic PWR is shown in this figure. A picture, we can see the reactor pressure vessel with the core inside and the control rod drives above, the pressurizer, the steam generators, and the pump recirculating the refrigerant, the coolant in the primary system. So the first transformation in Karen is to include the steam generators inside the reactor pressure vessel. The second change is to include the pressurizer. We eliminate the pressurizer as a component, but we include it at the top of the pressure vessel. So we can see that we have a pressure vessel, but the upper part of the pressure vessel has a steam dome like a classical pressurizer. What we don't have, there are heaters or sprinklers, classical or typical of PWR. The following change is to eliminate the pumps and to produce the circulation by natural circulation, because the steam generators are higher to what happened in a PWR for removing the decay heat removal. But in Karen is designed to use to remove full power.
Dario, we cannot hear you. Are you still there? Hello? Dario? Sepertinya ada masalah dengan internetnya ini. Okay, we are still waiting for Dario. Bapak Ibu sekalian, mungkin saya akan memberikan. Oh, Dario, are you okay?
I apologize.
Don't worry.
The connection failed. Could you tell me where you missed me?
Yeah, you told us about the simplification. Please, you can show us your share screen, your PowerPoint.
We'll go back.
And next. Okay, you can explain from here.
Okay, so one of the changes was to eliminate the external pumps and to use natural circulation for the coolant in the primary loop. The next change is to integrate the control rod drive mechanism inside the pressure vessel, as the pressure vessel is taller than a traditional PWR pressure vessel, and we have space in the upper part of the pressure vessel. So here we can see the operation of current 25 as, or a general current as an integrated PWR. So let's see the distinctive features of current. First is the integrated primary cooling system, which we have seen before. We are using natural circulation for cooling, so we don't have pumps in the primary loop. We use self-pressurization. Self-pressurization means that we have a steam dome in the upper part of the pressure vessel, but we don't have active heaters or sprinklers to control the pressure. The safety systems rely on passive features, and we have a 36-hour grace period. What means this? That these passive systems have a capability to keep the plant safe for 36 hours, assuming a single failure. So they are redundant, and assuming that one of the safety systems fails, the other is capable of keeping the plant controlled during 36 hours. The grace period, this time, can be extended by simple systems supported by autonomous systems that provide core and containment cooling and reactor pressure vessel and spent fuel pool refueling. What this means? We can use the fire trucks to extend this grace period as long as we want. To develop a reactor, we have to build many facilities to get the technology. I am just showing some pictures. We can see a critical facility. We have developed a critical facility because we have experience in heavy water and research reactor neutronics, but we wanted to test our tools with a PWR core. We have built high pressure, high temperature loops for testing the natural convection, self-pressurization, all the dynamic of the primary system. We have developed other circuits related to the control rod drive mechanisms, the fuel elements, traditional tests needed to check the technology to allow the construction of a prototype. So what is the aims? What are the aims of the prototype? The aims of the prototype provide basis for the commercial nuclear plant. Also, to facilitate the licensing process, the commercial nuclear want to have reference plan where we can base our demonstration of the commercial plan in an operating plan that shows the performance and how the system behaves. Also, to generate developing abilities within the Atomic Energy Commission of Argentina and its associated companies and the private industry in Argentina. The aim was to develop suppliers in Argentina, and we have spent money not only in the construction of the prototype, but in the same budget, we have money to develop the local suppliers for the construction of different components, like, for instance, the reactor pressure vessel. To facilitate also the export of nuclear power plant in a competitive market, like the previous experience we have had with research reactors. So, let's talk about Current 25, that is the prototype of Current. It's the first nuclear power plant fully designed in Argentina that is under construction. It's a PWR type. The gross electricity production is 32 megawatts electrical, is a bit higher than 25. The thermal power of the core is 100 megawatts. It's an integrated primary system, natural circulation, self-pressurized, use enriched uranium fuel, passive safety systems, and the operating cycle length is of 14 months. This length can be changed, but in the Argentinian case, we have decided for the prototype a bit shorter length than the PWR of 14 months for the prototype at the startup. This can be changed later in the following cycle. Let's talk a bit about the passive safety systems. We have a picture here. We can see, of course, the shutdown system at the control rod bars that falls by gravity. We have also a diverse shutdown system. The system 2 is a makeup tank that introduces a boron solution to stop the reactor. The Argentinian regulation requires to have 2 diverse shutdown systems. This is not traditional in PWR, but according to Argentinian regulation, we must have 2 diverse shutdown systems. The containment building is a pressure suppression type. We also have a medium pressure injection system. It's an accumulator type. A passive heat decay removal is a isolation condenser type. Of course, the relief valve, etc. I have mentioned that we can extend the grace period, and for extending the grace period, we have many connections allowing to refill the pools or inject from a fire truck directly into the pressure vessel, or also to cool the different pools inside the containment to allow the system to keep refrigerated and after the grace period. We can also make a spray in the containment to reduce the pressure and all the classical things to handle an accident using fire trucks or external autonomous systems. This was something that in the prototype was added after Fukushima. We were designing and even during the license process, and Fukushima happened. So during the license process, we have added to the prototype all these features and was part of the changes we have made after Fukushima accident. One thing that was very important for us to explain to our regulatory body was the strategy to implement the defense in depth principles for safety. Who are familiar with nuclear know the different levels of defense in depth. This is a bit technical. I apologize if someone is hard to understand, but it's very important to, when you design an innovative reactor, to have this strategy very clear, because the regulatory body requires to understand properly how you will handle and how you will classify all the systems. So I will explain this later, but we have the different levels of defense in depth, and we have addressed all these levels in the early design in CAREM as part of the strategy to handle the different events that could happen. The first level of defense in depth is, I will say it with other words, is to avoid having an incident. So the first things you try to do is to avoid having a problem. In CAREM, we have things related to this. For instance, natural circulation. Having natural circulation, you don't have a pump that could fail. If you don't have a pump that could fail, certain events that are typical in the PWRs, like pump failure, are avoided. So you don't have to handle these events. So the risk is reduced because there are things that doesn't happen. We don't use neutron absorbers dissolved in the coolant like boron. Other problem that you must avoid when you operate a classical PWR is to be careful to not produce a dilution of the boron in the coolant. If you don't use boron, you avoid this problem and you eliminate this, one of the events that can produce reactivity insertion by boron dilution. Other important thing is that having integrated primary system, we don't have the main lines of the primary system that can produce a large loca. We have small lines connected to the primary system, but these lines are very small. The diameter is below or up to 1.5 inches. So if these lines fail or break, the loss of coolant is very small, and we don't have the problem of large loss of coolant. We can see that these losses are so small that can be even handled by the control and volume system of the reactor, that is similar to the control and volume system of a PWR. The second level of defense in depth is related to when something fails, what can you do with the systems you are using naturally without requiring the actuation of the safety systems. So if you have something wrong, but you can handle it just with the equipment that they are already working, this is what you do in the second level of defense in depth. In case of CAREM, we have one system that is very important, is a chemical and volume control system. This is a system that is similar to PWR, but due to CAREM characteristics and having very little loss of coolant events, because we don't have large pipes, this system is capable of keeping the reactor safe without the use of safety systems. Also, if we lose the heat sink, this is a other traditional event considered in nuclear power plants. We lose where to evacuate the heat produced by the core. This system is capable of removing the decay heat by itself. So we don't need the use of a safety system we can handle this without the use of the safety system. This is part of the level 2 of defense in depth. These systems, they are not safety systems, but they are aimed to reduce the risk. And we have developed a classification that gives them some special characteristics to be capable of doing this task. Well, finally, in the defense in depth, you reach level 3. Level 3 is the level where you have the safety systems that are designed to deal with events and accidents. Well, the main characteristic of current is that we have passive safety systems, and they can handle the event for 36 hours. Let's call it the grace period. They are passive, but they are, let's say, classical passive light water safety system. So they are isolation condenser, accumulators, so systems that are already used and proved in large P or BWR. After this period, there is a period where we use active systems to keep the reactor stable and safe, like traditional PWRs used after a long time. We have also another characteristic, is that we think that both the passive and the active systems can fail. And we have alternative lines to handle the events considering failures or certain safety or active systems during level 3. We call this in this way. We have level 3A systems that can handle the problem, and if they fail, we have level 3 that can handle problems where you have a problem and safety system related to the problem fail. Related to this, one of the important things is that we have a second shutdown system. So even in the failure of a shutdown system, we have a second shutdown system that can handle the shutdown of the nuclear power plant. And for instance, if the isolation condenser fails, we can depressurize the reactor and allow the accumulators to go into the reactor and keep the reactor cooling even with the failure of the passive safety system related to heat removal during loss of heat sinks. This is something very important in the strategy, and it's important to deal with the requirements and the things you need to do to construct and build these systems. Of course, if you know, the 4th level of defense in depth is related to the case that all the systems, all the things fail, and you have a problem that produces the melt of the core. And what do you want to do here is all the things have failed, is to avoid that this can affect the people. So we have provisions to deal in case of multiple failures and to avoid the impact in the people. There are classical ones like the hydrogen control to avoid explosions. We have the capability to cool the lower head of the reactor pressure vessel to keep the core inside the pressure vessel by cooling from outside the pressure vessel and keep and return the corium inside the pressure vessel. We can add some components to the pressure suppression pool to increase the retention of the radioactive products inside the suppression pool, and to avoid the release of them to the environment. So all this was very important because having a new design, we cannot apply traditional safety approach for the licensing of the reactor. So this methodology and this was very important to be developed to a new reactor. This was based in harmony with the IEA SSG 30 and IEC 61226. So using this, we have developed a system classification that is based in all the functions related to the safety functions, and that provide the criteria for classifying and dealing with all the things related to the safety, based in the principle on defense in depth and the way that this principle is used to cope and mitigate initiated events in current design. This was a very long task, and the regulator was very focused in reviewing and dealing with this approach as part of the licensing of the prototype. So let's talk a bit about the prototype construction status. We can see here a picture of the site. This picture is from the beginning of the year. Unfortunately, due to the COVID-19, activities at the site were stopped for several months. We have resumed activity this month, but we have a long stop in the construction at the site. Activities remain in engineering and construction at factories, but were strongly affected the construction at the site. But fortunately now activities has come back to the site this month. So we can see here some pictures of the prototype building. Well, the construction of the civil work is about 62% progress, based a bit more now, but not too much. And we can see here in the pictures. The containment liner is the part of the containment used to assure that there are no releases from the containment. It's a steel liner, is 83% built. We can see different pictures and at different stages, and we are close to finish the upper part of the liner to allow the finishing of the containment after that. The balance of plant, the turbine and the other part, advanced also. The total progress is about 63%. We have more than 90% of the equipment already procured and construct. For instance, we can see in the upper left-hand picture the turbine building, and inside what we can see is a turbine is not already mounted, it's just stored at the side but not yet mounted. This turbine is a turbine that was built by Siemens in Germany, and well, it is already at the site. One important thing for us in Argentina related to current is that this is the first time we are building a nuclear power plant pressure vessel in Argentina. And this is an important supplier development. And we can see here some pictures of the construction of the pressure vessel in Argentina. We are constructing the pressure vessel locally, but we cannot do everything in Argentina. So, for instance, the forges were bought to an European company, an Italian company, and we make all the construction, welding, etc., of the pressure vessel. So these are other pictures of the pressure vessel parts. We can see some typical pictures of a PWR pressure vessel. This pressure vessel is basically similar of a PWR, but with some difference to incorporate the steam generator inside the pressure vessel. Other thing we can see are the steam generators, that they are different than traditional PWR steam generators. This was also an important development. The advance is 48%. We have already produced locally the tubes of Inconel 690. They are longer than traditional PWR tubes, so we have to develop a special oven to do the thermal treatment for these tubes. We are ready to finish the contract for the construction of a pre-series steam generator, and after that to start the production of the modules to be installed in the prototype. This is also done by a local company in Argentina that is also a supplier development. Other important things we are building are the fuel assemblies. We can talk a bit about the core. The core is a small core. It has 61 fuel assemblies. The active length is 1.4 meters. I apologize. In Spanish, we use comma instead of point as decimal separator. The maximum enrichment is 3.1. And okay, this is under development, and the progress is 53%. The fuel assemblies are under production, and the pellets are in a pre-production stage. The uranium, the enriched uranium is already procured, and we already have the enriched uranium for the startup of the reactor. So, the prototype is a way to demonstrate and to improve and check the technology we are developing. We expect, and we have already learned a lot from the construction of the prototype, and we expect to learn more when we finish it and we start the operation. But it's a step to produce a commercial unit. It's an important step because it's very hard to design and build a new plant just from without testing anything. So in our case, we have learned a lot already with the construction we are doing, and we expect to learn more when we finish the construction and we start the operation of the reactor. So the commercial unit will be based on current 25 prototype. It's very important for us the lessons we can learn for the construction of the prototype. Recently, our the operating company, Nuclear Electric Argentina, NASA is not the American NASA. The utility in Argentina is called NASA. Has created a working group for SMR evaluation and is planning to join our organization for future development. So, a commercial plant will use the economy of scale. The power of the module of the commercial plant is not 100 thermal megawatt, is of 400 megawatt thermal each. So this improves the economy for the scale, using the scale of the plant. When we have chosen the size of the prototype, we have been careful to choose a size that is representative of the commercial one, but that reduce the investment of the prototype to facilitate the construction and the testing. We will use also the economy of multiple units, learning curve, cost reduction in owner cost, engineering, equipment, and construction. So we are designing a module of 400 megawatt thermal, but we are considering to have more than one module at the same nuclear power plant. And the other thing we are considering is to allow the construction and commissioning in stages. For instance, if we will have several modules, to allow to construct in an ordered way to start the production with some modules before to finishing the whole plant. So this will allow to have early revenues due to electricity sales at the first unit start. This will allow us to easier meet growing demand, more flexibility to complement renewables energy sources, more flexibility to be adapted to site requirements. System and components will be shared between different modules. And one of the things we have also considered, but is not currently used in the present design, is to use some assistance for the flow in the primary system for, let's say, an internal pump to increase the flow and the power of the modules. This is something we are considering, but we are not using now because it's a development it's not yet proven for us, and it's not clear that will be economically beneficial. So we are considering, we are not discarding it, but it's not what we are focused on today. Well, I will show you one nuclear power plant we have been designing in the last year. We call them Canem 480. It's based in Canem 25. It uses 4 reactors of 400 megawatt thermal each. Each module has each containment. The layout for each containment will be based on Canem 25, but it will have some difference due to improvement in the designs. For example, as I have told you, during the licensing of current, we have to make some changes based on Fukushima lessons. These were done trying to not change too much the early design. For the commercial unit, we are optimizing this based on the lessons learned on Fukushima and during the construction of the prototype. We increase the power of each reactor, the economy of size, shared system and component, and of course, optimization of the safety design, commissioning, construction, stages, etc. We will have two parallel nuclear buildings. Each of them will house two reactors with their corresponding containments, a spent fuel pool between them and the nuclear system of both reactors. The auxiliary building will be located between both nuclear buildings. It will house shared system and services, the main control room, the auxiliary control room, and the administrative office. One important thing we are planning and developing is to consider the whole plant as a unique plant. Let's say we have different modules, but they are controlled as one plant in one single control room. One balance of plants with two turbine generators each, with the capability of processing the steel coming from two reactors, more flexibility to complement renewables energy sources. So this is a conceptual layout of this plant, and we can see the four modules, two spent fuel pools, one balance of plant with two turbines, and a main control room and other shared service building common to all modules. Well, to finish, I can show you what are our cost estimations related to this nuclear power plant. The fuel cycle cost will be from $7 to $10 per megawatt electrical hour. The range depends in cost of the fuel that can change during the time. The overnight cost of a module of 120 megawatt electrical is $760 million, American dollars. And the overnight cost of a multi-module current 480 is $2,300 million US. We are currently working on the calculation models to analyze the financial benefits of some changes based on the experience gained from the prototype. Simultaneously, the financial database is being updated by gathering the prototype construction real values and optimized construction costs. So we are using all the information we are getting from the construction of the prototype to improve the estimation of the cost of the commercial unit. Thank you for your attention. If you have any question, I am available.
Thank you, Dario. It's very interesting presentation. Well, there are a lot of questions to via chat in YouTube or in Zoom. So, but I would like to invite several persons. They are representative of the audience from senior level lecturers, even a member of National Nuclear Youth Community. So, but I would like first to ask Dr. Ferhat Aziz, the former Deputy Chairman of National Nuclear Energy Agency, to ask you or to give comment. Please, Pak Ferhat.
Thank you, Pak Jarod, for giving me the time to ask some questions. First of all, Dr. Dario Del Mastro, congratulations for your very nice, informative and encouraging presentation on the current status of KERM 25. It is interesting to note that Argentina was the first nuclear power plant country in South America when you built the first Atuchawan in 60s and 70s. I'm sure very soon Argentina will also be the first SMR country, even in the Americas. So this is very encouraging development that you and your team showing us. Of course, there are many others SMRs developing around the world, like the HTRPM of China, the KLTS-40 of the Russia. But KERM is indeed among the leading design that is now getting a lot of attention from researchers around the world, including from us in Indonesia. I would like to have to raise some questions, however, based on your presentation. That is, I noticed that in your fuel design, you make a design of hexagonal letters of fuel rather than square letters as usual. Is there any particular reasons to doing that, or you have any other reasons? That is the first question. Yeah. Okay, go on. You can answer that.
Yeah, this is it's a quite traditional question.
Yeah.
There is one reason, is that in the prototype, but also in the commercial, the core is smaller than a traditional PWR core.
Yeah.
An hexagonal fuel element allows to have a better shape of the core, closer to a circular shape. So we have decided to use the hexagonal shape to have a more compact, a better shape of the whole core.
All right. Yeah, it's understood. Yeah.
That's the reason.
Okay, that's understandable, because usually if you have tight letters, then you have a rather harder spectrum of neutrons. So anyway, my second question is, I noticed that you have some fuel enrichment capability in the country. And I also read that actually your Atucha 2, I guess, PHWR already use 1.9% fuel enrichment. Now in this design of KERM, you said you are going to use 3.1% enrichment. My question is whether you produce your own fuel, you enrich your own fuel for this KERM design, or you procure it from other countries.
Okay, it's a very good question.
Yeah, very interesting
we have
questions.
We have a nuclear facility for enrichment, but it's at laboratory scale, the one which is working now. We have a prototype plant, but it's not working today.
Oh.
We have only the enrichment. We have enriched uranium in the last years, but at the laboratory means you have in enrichment plant, you have, let's say, one module repeated many times. Well, we have a group of modules we have used in the last year to improve and update the technology, and they have enriched uranium in the last time, but we are not producing commercially, locally. For the prototype, we have bought the enriched uranium from different countries, Brazil and other countries, but there is something that is important for us. Having this enrichment capability, it's easier for us to make deals with other suppliers. So having the technology and the capability allows you not only to produce, but also to make deals easier with other suppliers. And the decision was that we want to have the technology, we have improved our technology in case we have problem with the supplier, but if we can get a reasonable price for the supply, we are not a very large country, so we have to choose where to invest our money. We cannot build everything. If with the laboratory we can make the contracts we need, we will not make the whole factory if we don't need it. But we want to have the technology to be because it is important that if we can, we offer a product, we must be capable of offering the fuel. So we have the technology, we have the factory. We are not operating it now commercially because we can get the supply from outside, but we keep the capability of doing that. Other reason is that our production for this at Tucha and Karen is a small production. And in enrichment, if you produce little, the cost is higher. So if we can get a good procurement contract with the supplier, we use it. But we need to be ready if we increase our production and we need more supply to be capable of to produce the enriched uranium to supply all the things we can produce.
Okay, maybe one final question.
Yeah.
All right. This time it is related to safety. You mentioned in your presentation that the lower part of the pressure vessel you design such a way that it will be intact in any situation, and therefore in case of accident the core will not melt out of the pressure vessels. Do you do you consider that in case of such thing happen, and probably you need a core catcher underneath, because this is, I think this is advised or recommended by the IAEA in a new design, that they have at least some mechanism of like a core catcher in case of corium melt. What is your opinion on that? Thank you.
This is an SMR.
Yeah.
As you can see, we have less power. So the pressure vessel is relatively larger than in a traditional PWR.
Mm-hmm.
So in the lower part of the pressure vessel, the area available to spread the core is larger. So we have made our computations and we have shown that we can cool the lower part of the pressure vessel from outside to be sure that we can retain the corium inside the pressure vessel, avoiding to reach the floor. The problem, for instance, of EPR is that the power of EPR is so large that they need a larger area to spread the core. In our case, due to be an SMR integrated, the pressure vessel is higher, the area is higher, and we can do that internally. I think that this can be done also by other designers. It's related to be an integral type reactor with a larger pressure vessel, well, that is the reason. So we have incorporated this core catcher, but we can do that using the lower head of the pressure vessel as the core catcher itself.
All right.
Okay, thank you. Terima kasih, Pak Ferhat. And the second, thank you very much, Pak Ferhat. The second person, I would like to invite Professor Abdul Waris from Bandung Institute of Technology to give comment or questions. Please, Pak Professor Waris. Hello. Are you there?
Halo, Pak.
Silakan, please.
Pak. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Good morning, Dr. Dario.
Good morning.
First of all, I would like to thank you for giving us inspiring talk. We are people from certain part of the globe, have a strong capacity or capability to develop their own nuclear power plant. I think it's very inspiring for us. According to your presentation, Kerim's 25, the first nuclear power plant that totally designed inside Argentina. I think it's okay, right? The design, as we listen from your presentations, very attractive with cutting-edge technology. I'm interested in one point, especially regarding you have integrate primary and secondary circuit or cooling system. You integrate in pressure vessel, so no pumps and no separated steam generator. This means that you have a reactor with 100% natural circulation. Can you explain more to us about this scenario or this technology? That's my first question.
Well, when you have an integrated design, you put all the components inside a pressure vessel. So the pressure vessel is larger and heavier than the same pressure vessel for PWR. So that's why these SMRs have lower power, because one of the things we have studied and that limits the power of the modules is to have a pressure vessel that can be built in a cheap way. You can build larger pressure vessels, but then you have less suppliers, more difficult to get the components, to do the constructions, welding. So the cost doesn't reduce with the size, increase with the size. So our target was to get the pressure vessel in a size that can be built in an effective and cost-effective way. So that's why we have chosen 120 megawatt electrical for the module, is due to related to limit the size of the pressure vessel, not because you can't build a larger one. You can build larger, but they are more expensive because you have less suppliers and it's harder to build this component.
Okay, thank you very much. I have another one question, okay? How about processing of spent fuel? I mean, do you choose recycling process or one through cycle in your Kerims reactor?
Well, I will tell you that this is not a decision of Karen. We are using now the policy of the country. Okay. The actual policy of the country is what we call wait and see. Okay, wait and see means we are not reprocessing, but we are not throwing the spent fuel, because in the future it could be needed. This time in Argentina, like in most countries, you store this spent fuel. Today it's quite easy and economical to store spent fuel in a safe way, and we are waiting what happens in the future. Every day you wait, the spent fuel is less radioactive and could be handled easier later. But at this time, the cost of recycling is not economical beneficial compared to having a one-through cycle today. But we keep the option of recycling in the future if needed.
Well,
thank you.
Thank you, Pak Waris. It's very interesting. So many countries have the same position. Wait and see, I think. Well, the third person, I think, younger than the two person before. I would like to ask Dr. Muhammad Subakti from Batam. He is engineer and also as a researcher. Please, Pak Muhammad Subakti or Pak Mehmet. Can you unmute?
Okay. Thank you, Jarod.
Please.
Okay. Yes, thank you for your presentations. We have a lot of information about current 25 from long story. Start from about first infrastructure on development of and design on PWR and PSWR. And also we have learned from your presentation about how your country develop and the nuclear knowledge. We have interesting on many aspects, but we start from the first questions about the thermal hydraulic aspect, how you can drive the natural circulation inside the reactor to push the coolant for the first operation in simulations. We know we have a study on natural circulation and also experimentals in our site. It's really very difficult to drive the buoyancy effect and also how to drive to circulate in natural scheme of circulations. And it's related to the next question. If we compare using pumps, what is difference between the natural circulation or using pumps?
Okay. I will start with the natural circulation part. We have done a long development to check the natural circulation phenomena. You are right that natural circulation is very nice, but is you need to analyze it very well and you need to be very careful. We have done a lot of work related to natural circulation. Even as I have shown, we have to build a high pressure, high temperature loop, full height, to analyze natural circulation and combine with self-pressurization and the steam generator configuration, etc., and to analyze different aspects. Fortunately, of course, when you build a high pressure, high temperature loop, even you have full scale, it's not the same as a reactor. You must build a reactor to check, but it allows us to check our tools and to see many things, and we were very confident. We are very confident that the behavior is smooth and stable. We have done a very large analysis. We have get consultancy from people from Netherlands and Europe related to stability of natural circulation, people from Delft University in Netherlands that were, they have the experience and have analyzed a boiling water reactor with natural circulation in Netherlands in the past. We have people working with us that were in charge of dealing with the studies for NRC, for natural circulation and stability of the ES-BWR, the large BWR with natural circulation. We have spent a lot of resources and money analyzing the natural circulation, and we are confident of that. Of course, using natural circulation implies things. Implies that we have to reduce the pressure drops, so the pressure vessel is larger because you have to get the system to flow with less restrictions. But we have analyzed also the use of pumps, and you can formally increase the flow rate and the power, but when you see the cost, the improvement is not so clear. When you start to add the cost related to the pumps and all the things you need to arrange to have the pump working and to deal with the pump problem of losing the pump and all the things, and you make an economical evaluation, you see that there is not a big difference with using pumps in these modules. So we are not this. We can consider for the future assisted circulation. We have tried using internal pumps and even jet pumps, like in boiling water reactors, but the improvement is not so big, considered from an economical point of view. So, and you have more things that need to perform properly. So our decision is we are more confident dealing with natural circulation, testing it. We feel that we will have something that will be competitive using natural circulation. But we are open to consider in the future assisted circulation, including internal pumps. We have even done some experiments using jet pumps, but we decided to keep natural circulation for the prototype and the first commercial models.
Okay, thank you for your explanations. One more question, I think is still related to the natural circulations. We imagine when we start up the reactors from 0 until to full power of 100%, what time it takes to reach 100% of power from 0?
Yeah, well, there is something that is important first, and I will associate with your question. As we don't have a primary pump, we have, I didn't show it, an external boiler to allow the non-nuclear heat up before going critical. It's a PWR, so you cannot get critical at ambient temperature. You need to heat up first the reactor. So this is something that is not been shown, but in every natural circulation system, unless for the first startup, when you have decay heat, this is not so important. You need to have an external heater to heat up the reactor before going critical. After that, the time needed to start up is about 12 hours. And it's more related to the temperature ramp allowed to by the pressure vessel to avoid thermal stresses in the pressure vessel.
Okay, thank you, Pak Bekti. Then the fourth person I would like to invite to have comment or questions, Pak Alexander Agung. Dr. Alexander Agung is the lecturer from the Gajah Mada University in Yogyakarta. Please, Pak Alexander Agung. Hello, Pak Alexander Agung. Okay.
Yes, hello. Thank you, Pak Jarod. Thank you, Professor Dario, for your interesting presentations about the KERIM 25. Here I would like to ask you two questions. The first question is related to the self-pressurization. You mentioned that in KERIM 25, you eliminate pressurizers, and instead you're having steam dome on the top of the pressure reactor vessel. But considering that the KERIM 25 is a PWR based reactors, how do you maintain the steam inside the pressure vessel, and also how do you maintain the pressure of the system if you don't have any heaters or spray or sprinkles? That's my first questions.
Thank you. It's a very good question. Self-pressurized is a tricky word. You have to produce vapor because you have condensation in the structures of the dome. So in the way we control the pressure, because the pressure is controlled, is we don't have heaters and sprinkles, but controlling the balance of power between the heat produced in the core and the heat removed in the steam generator, you control the energy inside the pressure vessel, and you control the pressure in the reactor, primary system. So what happened is that there is a small amount of vapor produced in the core, and controlling mainly the pressure, the power you remove by the secondary system, you control the pressure of the primary system.
And the second question, Pak?
Okay, thank you. And the second questions, you mentioned that in Karam you got many simplifications. It means that, and also you use smaller pipes, for example. So it means that you may have, I presume that you may have a lower probability of large break LOCA, loss of coolant accident. But from your presentation, I noticed that in defense in depth level 3 or 4, there is an corium retention with cooling inside the pressure vessel. So I would like to ask you, what is the limiting event or postulated accidents in Karim that may lead to a severe accident?
Well, the corium, well, you remember that Fukushima happened. So yes. Even we have shown that we can meet all the requirements without the core catcher. After Fukushima, we have implemented these capabilities in order to complement the reactor. At this time, the regulatory body didn't require us to have it, but they asked us, what could you do in case you have all the systems? It's okay, but suppose you have a core melt. Yeah. Your design is okay, but assuming you have a core melt, what can you do? And we have added this core catcher, and even we have added a venting from the pressure suppression pool to allow containment extension of the life of pressure control in the containment, and many things. You can say you don't need it, and of course, if we need to demonstrate the safety, probably you don't need the core catcher. But after Fukushima, it sounds like a good behavior to try to include these things if it can be handled in a cheap way. In our case, to implement this core catcher was very, very inexpensive. So it was not really expensive to include this feature. So there was no reason to avoid it because the cost related to include it is very small. And the confidence that gives to the whole thing is important because it's something diverse. It's something completely different from the other. So if everything happens and the other thing fails, this is something completely different. And the cost associated to implement it was very, very low, very low.
Okay, thank you very much.
Okay, thank you, Pak Alexander. The youngest one, there is one student. He is the member of National Nuclear Youth Community. I would like to invite Hafiz Akbar from Yogyakarta. Please, Hafiz, you can ask anything you want to know.
Okay. Thank you for the opportunity, Mr. Jarod and your honorable Mr. Dario. Assalamualaikum warahmatullahi wabarakatuh. Good morning for Mr. Dario and good evening for the other. Firstly, I was impressed with Argentina's development in nuclear technology. And I'm from Komin, Yogyakarta, as a representative of the nuclear youth in Indonesia, including the students and young nuclear researchers in Indonesia. Okay, so first, I want to ask about youth and regeneration. Is youth very influential in this nuclear company, sir? Or at least, how do you view the value of trust in youth in dealing with the nuclear project in Argentina? Okay, that's the first question. I think. Thank you, sir.
Excuse me, I will try to check if I properly understand. You were talking about the influence of young people?
Hafiz, can you tell that?
Excuse me?
Hafiz, please,
yes?
you ask once again. Maybe
Okay.
Dario didn't understand what you said.
Okay.
I missed one word, so if you can repeat the question to be
Please
sure
repeat your question.
I answer properly.
Okay. I want to ask about youth and regeneration. Is youth very influential in this nuclear company, the SNEA? Or at least, how do you view the value of trust in youth in dealing with the nuclear project in Argentina? I think the influential of young people in nuclear technology in your country, sir.
Okay, I understand. Well, let's tell you something. In the last 15 years in Argentina, we have a very important increase in young people working in nuclear. We have the problem that 15 years ago, our average age was going high. There were a lot of time where there was not so many people going into nuclear. At that time, I was young. Now, no. And so in the last 15 years, we have incorporated a lot of people in nuclear. Our people working in nuclear has almost doubled in the last 15 years. So we have a new generation of people going on in nuclear, working mainly in these new projects. And as I have told you, for the enrichment plan, for instance, one of the reasons was that the operators and the people who have developed the enrichment plan were getting old and close to retire. So we have focused in incorporating new people who learn the technology and can give us a future, because if you lose the people and you don't have young people, you have no future.
Okay.
So in the last 15 years, fortunately in Argentina, we have had an important growth in young people working in nuclear, not only in reactors, but also in the other areas related to nuclear. This was something that it was decided by the government about 15 years ago. So Fortunately now, we have an important participation of young people in nuclear, and we feel that for some time we have an interesting future. Of course, we need to keep going with this because it's something that changes every day.
Okay, thank you, Dario. Hafiz, do you still have one question? Short question, please, if you have. No?
Yes, sir. I have one question again. The second question.
Yes.
Please. Please unmute yourself. Oh.
Okay, thank you. I'm sorry, I can unmute myself. Okay. Thank you, Mr. Dario, for the first answer for my first question. And the second question is, me and Common Yogyakarta, as a young nuclear community, always strive to do intelligence and understanding in society. Can you give us a little motivation so that to socializing the nuclear technology for the people? Thank you.
Maybe you have we could not hear you because there trouble with audio. Could you repeat again your questions? Hafiz, please.
Okay, thank you. Mr. Dario, the second question is, me and Common Yogyakarta, as a young nuclear community, always strive to do intelligence and understanding in society. Can you give us a little motivation so that we can continue on this path and survive until we can continue the socializing activation for the people?
Okay. First, I will tell you something that is personal. I have 6 children, and one of my children is a nuclear engineering. It's a young nuclear engineer, and he's working in safety, and he has been working for the design of the reactor we have sold engineer to Brazil. He's working in Argentina. I have another that is a mechanical engineer, but is also working here. They are very young. They are my family is related to your question about young people going into nuclear. One thing that is important is that it's my experience. I don't feel that this is something that could be worldwide, but in our case, the family and the local society is very important. If you have the people and the family involved in this, and it's not something that is far away, and the people is close, is part of the nuclear, it's easier to understand. I will give you an example. Now, by law, we have public hearings with the public for the facilities. For the enrichment facility, we have a public hearing. And of course, there were organizations and people that they don't agree with nuclear. But it was very important that the enrichment facility was close to a small town, and the local people of the town participate and work in the facility. So there was a very strong support of the local people and the local community to nuclear because it was part of the community. It was something for them. And this is important. Not to get nuclear away from people. Nuclear must be part of the society. People working in nuclear must be part of the society. it must be open to the people. People need to feel they are part of nuclear.
Well, it's very important, I think, your last quotes. Nuclear is part of the community. We have to
It's very important.
Yeah.
Sometimes you try to keep them as something special. We are better. We are more clever. We are something. No. You must be part of the community.
Okay.
Your family must be proud of you. Your children must be proud of you, and the friends of your children must know about that. They need to be natural to them, not something strange.
Okay, thank you, Dario. It's very, very interesting that you are a teacher, a best teacher, I think, and not only on the nuclear, but also on the how to motivate all of us. Thank you. But we have many, many questions from the audience, from YouTube and Zoom. But I can make a three question. You may explain in a short sentence. The first question about the safety. Indonesia is a country that, we suffering the earthquakes and tsunami. How can you, for example, if someday Indonesia want to use the current technology, is it suitable for Indonesian, like in our archipelago country, so many earthquakes and so many natural disasters? This is the first question from the audience. The second question is about the CARM. You are proud of the CARM 25. How many percent of the parts of that CARM coming from your country, and how many percent from outside, from import, for example? The third one about the economy. So many audience want to ask you about the cost, although you already said that this is the prototype. But why you want to build the SMR? This is the question from YouTube. While to get the permission from the regulatory agency, maybe the difficulties, the complexities is the same with the large NPP. Why you want to build the SMR rather than the large NPP? This is the three questions from the audience. Although,
could you repeat
the last question?
The first one.
The first one. Indonesia is a country that we are suffering many natural disasters like earthquakes and suffering the tsunamis. If some days, for example, Indonesia want to use that technology, the current, maybe the current 120 or something like that, is that technology suitable for the country with so many natural disasters like earthquake and tsunamis? This is the first question.
The first one, okay. What I feel is that this technology is not only current. I think that there are other SMRs that follow the same trend. Using these configurations, integrated configurations with passive systems and low power that facilitates the cooling after an event are very suitable for places where you can have external threats, because you can have things needed to make this sure very easy to protect. You don't need to assure electricity provision of a special energy, these kind of things, and this is strongly related to to be an SMR means to have low power and a different configuration that facilitates the implementation of these passive and simpler ways of cooling. One of the things we have learned is that even in these disasters, there are things that can work. After some time, you can get fire trucks, or you can get some things in some places or mobile things that need to be autonomous, don't need to depend on established grid or an electrical grid. And these things, small things that can be stored in safe place and transported easily, are enough to extend the security of these plants as long as you want. And this is very important. Related to a seismic, you see that there is not a big difference with the other, but the only difference is that they are smaller. So sometimes this simplifies the seismic requirements, not the requirements, the way to implement the requirements.
Okay. And the second question is about the, well, you are proud with the CARM 25 program. So how many percent of the, maybe the parts of this CARM coming from Argentina made by yourself, and how many percent import from other countries?
We have, let's say, this is a rough estimation. We have not yet finalized, but we have 2/3 locally produced and 1/3 imported.
Okay.
And why 1/3 imported? There are things that if we want to do by ourselves, they will be not competitive because there is industries that need to have an important production to get these things. And for instance, the pressure vessel, we weld it, we mechanize it, we do all the things, but the forges, we have bought the forges in Europe. The turbine technology is a technology that is available worldwide, and you have special people that can do very good turbines. There is have no sense you develop a new turbine when you can buy in a easy market competitive turbines. And one thing that is very important, small turbines for SMR in the last decade has really improved a lot, not by nuclear, by the other use in other industries. So if you can use components from other industries that are cheaper, this is very important to reduce the cost associated with SMRs.
Okay, thank you very much. And the last one, the question is from the audience, from the YouTube. He asked about to build the small modular reactor and the large NPP has the same difficulties to get the permission from the regulatory agency. Then why you choose to build the SMR or prototype SMR rather than to build the large NPP?
Well, you are right. Formally, the process is the same. Well, the idea is in Argentina, there are not so many places where we can build large nuclear power plants. To find a site for large nuclear power plants is possible, but it's not easy to find a place for a large nuclear power plant. The electricity in Argentina, the grid, has a very important concentration in demand and production in certain parts. And the grid wants small plants to be distributed to balance the grid. So there is a need or requirement to get smaller plants that can be placed in different parts of the country, because if we don't do that, the cost associated with the transport and the grid costs are increasing too much. So the cost of electricity is not only the cost of the plant, also the cost associated with the grids and transport could be very important. And in Atucha site, I remember when we went to talk with not the regulatory body. To build a nuclear power plant, you need to get a lot of permits. The regulatory body permit, the permit to use the water, the permit of the local state to use the land, the permit of the electricity authority to be connected to the grid. There are a lot of permits. When we went to talk with the grid, they were very happy to have a small plant connected to the grid. They are very favorable to have smaller plants connected to the grid. They facilitate then the interconnection at the design of the grid. At the beginning, we were worried because they said, well, they will not consider us because we have a small nuclear power plant. And they were very interested because they said, having a small one, we can make better connections to the grid and we are improving our grid. So from their point of view, they are very interested on that. From the regulatory point of view, I agree with you that the steps you have to perform for a large nuclear power plant or for a small nuclear power plant are formally the same. But when you get a commercial unit, you will use a lot of material from the first unit to license the second unit. So these things will not be so important if you can get the other benefits.
Okay, thank you very much. I have a last questions. When do you think this current 25 will be in a full operation?
Well, that depends what you mean a full operation. We are expecting to, let's say, it's a prototype. So we have some steps we plan to do. First, before going critical, we will have longer period of testing before going critical. We will test, for instance, with an external heater, we'll test natural circulations and passive safety systems in the reactor without using the core at the plant before going critical. This is part of our testing that we will do with the prototype before going critical. After that, we will go critical with the approval of the regulatory body. We expect with the COVID-19 we have some delays, but we expect that we can get critical in 2023, but that will depend on how fast we can resume the activities in the, now our activities are not at full speed. So if we have more delays with the COVID, this could be delayed. And after we go critical, we will foresee we will have a 2-year period that we will be producing, but still in some way testing the performance of the nuclear power plant. So if you mean commercial in a full way, it will be 2 years later of a critical, of being critical. Of course, this will depend on the performance and the results we are getting through all this process that is very important for us as a process to get confidence and to get the product. It's a process.
Okay, thank you very much. The important thing is because this is prototype, so many things have to do. But I expect you will be, the Argentina will be an advanced country in the future, because after completed the CAM25, you will build maybe where you have program of CAM for 480, for example. Anyway, thank you on behalf of Indonesian Nuclear Society and on behalf of the audience, I would like to say thank you, Dario, for this very excellent presentation from you. Hopefully, many students want to ask you many things. Many audience also have many questions. Hopefully, you may have time in the future if we invite you again in our webinars. Again, thank you very much. Thank you.
Thank you.
Terima kasih Bapak Ibu sekalian, acara webinar ini luar biasa. Jadi kita sudah mendengar dari Pak Dario berbagai hal. Besok Badan akan mengadakan webinar lagi pukul siang hari terkait juga dengan SMR. Jadi ini kita juga bisa mendengar berbagai perkembangan di negara-negara lain. Saya ingin mengajak Bapak Ibu untuk melihat schedule kita berikutnya HIMNI. Ini adalah schedule kita. Hari Minggu malam nanti ada sharing YouTuber nuklir tanggal 20 September. ada 2 orang yang lulus dari belajar masalah nuklir. Kemudian tanggal 24 September ada perempuan bicara nuklir tentang reaktor nuklir bisnis batu topas. Nanti kemudian tanggal 29 ada Pak Muldoko, beliau berbicara sebagai Ketua HKTI terkait sorghum. Ini menarik juga. Dan 1 Oktober jangan lupa kita akan mendengarkan success story kenapa Bangladesh bisa go nuklir, membangun PLTN. Nah, ini adalah program-program kita bulan September dan 1 Oktober. Moga-moga Bapak Ibu sekalian bersedia untuk hadir dalam acara ini. Sekali lagi terima kasih kepada Bapak Ibu sekalian. Acara webinar ini sukses semuanya. Semoga kita bisa ketemu lagi di lain waktu pada webinar-webinar berikutnya. Terima kasih.
Terima kasih, Pak.
Sama-sama,
Terima kasih, Pak.
Terima kasih. Thank you, Dario.
Terima kasih, Pak Jarod.
Thank you very much, Profesor
Terima
Dario.
kasih. Assalamualaikum.
Waalaikumsalam.
Pak Jarod, Bu Jenny, semuanya.
Ya. Ini komun jangan ada juga banyak juga nih ya.
Terima kasih, Pak.
Terima kasih. Terima kasih Pak Jarod dan rekan-rekan.
Thank you Dario.
Terima kasih Pak Jarod.
Terima
kasih Pak Jarod.
Terima kasih Pak Jarod.
Pak Salim, Pak Utomo.
Assalamualaikum.
Sampai ketemu lagi. Ya.
Terima kasih, hari ini sangat menarik sekali Pak Jarod.
Ya. Masih ada yang menarik nanti Bangladesh
sekali, Pak.
Ya, Pak Ari makasih ya. Spesial luar biasa nih. Cocok jadi pejabat itu.
Dalam?
Cocok jadi.
Mantap Pak Ari.
Mantap Pak Susilo juga.
Ayo, ini mau di dapur. Padahal aku tuh goreng ayam dulu tadi saya baru pulang.
Ini ada Pak Edwin yang selalu hadir selalu di Pak Edwin.
Alhamdulillah. Mas Beti, gimana kabarnya?
Pak Mehmet.
Ayamnya baunya sampai sini tadi, gorengannya.
Lah iya tuh pulang kantor ya jam 9 atau jam 7. Aduh ini ngomong ya. Iya.
Tapi
biasa Pak Hari itu.
Udah nyaingi Pak Dimas jadi diplomat itu.
Saya lagi ke bawah Pak Jarod.
Pak Dimas saya bilang, ini kapan kita makan malam, Pak?
Tapi
matur nuwun Pak Jarod.
Matur nuwun.
Terima kasih,
Sampai
Pak
ketemu
Ari.
lagi, matur nuwun. Terima kasih untuk semuanya.
Terima kasih.